Now I'd like to introduce today's featured presenter, William Chueh. Will Chueh is an assistant professor in the Department of Materials Science and Engineering and a center fellow of the Precourt Institute for Energy at Stanford University. Professor Chueh has received numerous honors, including the MRS Outstanding Young Investigator Award in 2018, the Volkswagen BASF Science Award, Electrochemistry in 2016, the Camille Dreyfus Teacher Scholar Award in 2016, and many others. In 2012, he was also named as one of the top 35 innovators under the age of 35 by MIT's Technology Review. He received his BS in Applied Physics, MS and PhD in Material Science from Caltech prior to joining Stanford in 2012. Now I'd like to turn the floor over to Will.
Thank you, Joe, for the introduction. And it is my great pleasure to give you a brief presentation on the future of energy storage. So if you look at the cost of lithium-ion battery, for example, since 2010 it has declined by almost 80%, and the trend is only increasing. On the other hand, if you look at the cost of generating electricity renewably, that cost has even gone down even more. For example, for wind electricity since the 80s has gone down by 90%. And for solar, that has gone down by 99% in the past 2 decades. And if you combine the decline costs of storage and generation of renewable electricity, that leads to 2 very interesting questions. The first question is in the sector of transportation. So what are the remaining research and development needed to fully electrify and convert our internal combustion engine fleet to electric vehicle? And a greater question and a bigger challenge is for the grid. So can we combine this low-cost renewable electricity and low-cost storage and compete on cost with conventional electricity generated from fossil fuel purely on cost? So these are the 2 questions I'm going to try to give additional details. I will discuss them both from a business perspective and also a technology perspective. And let me just state the take-home message, which is you have to look at the problem both from the business side and the technology side. So I'll go over some details in the next 45 minutes. So let me start with a plot showing you the tremendous growth in EVs. This is plotting the millions of vehicles for the past 8 years from 2011 and projection into 2019. And you can see we sold our first million electric vehicle in 2015, then the second million in 2016, and now we have sold over 4 million passenger EVs, and within the next year, we'll add another million to that. The numbers are big, but they are very small compared to the global industry of 1 billion vehicles. So that tells you some of the opportunities going forward in terms of fully electrifying. And I don't think I have to highlight the importance of battery technology for transportation. So I think most people can appreciate the growth of EVs. Perhaps a harder problem to see is how energy storage is impacting the electrical grid. And here I'm showing you the global installed capacity for renewable generation. So this is showing in green for wind and in yellow for solar. And you can see over the past 18 years, the increase in this installed capacity of wind and solar has just been enormous. Now we're approaching approximately 1 terawatt of installed capacity for wind and solar. So the electricity grid is changing very quickly. And one of the key challenges is how does the grid cope with the generation of what we call variable electricity? So these are not resources which is available all the time. The sun doesn't shine all the time and the wind doesn't blow all the time. So how do we think about changing the grid to accommodate for this variable generation of electricity is one of the key challenges going forward. So let me talk about energy storage in the context of the electricity grid. These are plots showing the utility scale energy storage installation that is forecasting from 2017 all the way to 2026. And here on the left, we're looking at the energy storage in terms of utility. And on the right, it's the installed capacity for distributed energy storage. So utility means very concentrated. So these are power plant style energy storage technology. And on the right, these are distributed or home-based or business-based energy storage. And I won't get into the details of this plot, which is being distributed over many countries, but the key aspect is the trend. Energy storage is going to grow very rapidly, both at the utility level and at the distributed level. And the reason is actually quite straightforward. One easy way to deal with variable generation of electricity is to be able to buffer it with energy storage technology, such as batteries. So one of the key drivers for energy storage is policy. And being here at Stanford, let me start with California. So there are several very notable policies that is driving the investment in this area. For example, the mandate to have 1.8 gigawatt of installed storage by 2024, and more recently, to go completely carbon-free electricity by 2045, that was just announced 2 months ago. You can see similar initiatives in the policy area in Arizona, New York, Massachusetts, Texas, and many places in the US and globally as well. In the US, the state level policy, it is currently what is driving energy storage on the grid level. And this is going to be a very significant factor going forward in the growth of the industry. So let me give some specifics on battery technology. Battery, it is not the only technology that can be used for grid storage. I will talk about a variety of them later in the webinar, but just show you one example. This is for battery-based technology, and you're basically seeing almost zero installation and capacity prior to 2010. But because the cost of lithium-ion battery has gone down so much, you can see that the declining cost is almost matched with the installed capacity, which has really taken off since 2010 as well. This is a great start, but we're still very far from matching this to the 1 terawatt generation capacity I showed earlier from solar and wind. So this highlights the challenge we have to deal with. And I will talk about a little bit some of the technological and the business drivers behind getting the storage capacity to match up with that of generation. So let me talk a little bit about the application of energy storage in the context of the grid. So we can all appreciate how energy storage can help with transportation in terms of electric vehicle. The grid is a much more complex system. And you can think about the utility of storage in the context of the duration of storage. So how long do you have to store electricity for in order to tackle some of these various applications? And with recent applications, each application has a revenue associated with it. So this is driving some of the technical economic behind storage on, for example, whether utility companies will incorporate storage or not, or do they go with traditional means of providing electricity, for example, through natural gas power plants. So let's start at the bottom. On the level of seconds, you have things like startup of the grid. So you have to provide some initial energy if the grid was down and you have to restart it. The second one is frequency regulations. If you look at your electricity output, it is very stable, okay? But that only happens when demand and supply of electricity are perfectly matched. And sometimes it is difficult to match it, so you have to have some amount of buffering so that your electricity will come out at the right voltage and the right frequency, so 120 volt and 60 hertz in the United States. Then you go on to minutes. So these are what's called reserves. So to accommodate for variations in the grid, you have to have electricity that you can provide on a reserve basis on the order of minutes. Then keep moving up, you have what's called peak shaving. And this is corresponding to the fact that there are demands of electricity that is high and low in the day. And when the demand gets too high, this puts a lot of stress on the system, on the grid. So being able to shave that peak to decrease the peak requirement of electricity from conventional sources is important. And then if we move up even more, in the purple box, we talk about curtailment. So this is where there is so much renewable being generated, for example, from solar and wind, you can't use it all. And if you can't use it all, you have to start either dumping the electricity away, or you have to think about basically curtailing it. And this is a significant revenue loss for the electricity grid companies as well. And on the very, very top right, you have seasonal or long duration resource shifting. I'll talk a little bit about this as well. So you have different outputs of electricity from solar throughout the year. So we have high solar output in the summer and lower solar output in the winter. But the demand is actually somewhat uniform. So being able to shift, the ability to shift the electricity between seasons could also be very important and another important source of revenue. And if you look at this plot from left to right, it also shows you how important it is dependent on the penetration of renewable. So when the renewable penetration, if you want it to be 100%, you have to talk about seasonal storage. But if you only want it to be 10%, then maybe we can get away with just peak shaving. So let me show you one example of a typical 1 week electricity generation here. So here we have green, it's the generation of wind. And we have here in yellow at the top line, that is the total electricity load. So if you look at the green here from left to right, you can see it's highly variable. It can be almost zero at times, and it can be very large at other times. And if you look at the low profile, the up and down reflects the cyclic demand of the day, higher during the daytime and lower during nighttime. And where you have a peak demand and low wind output is where you have to provide electricity from something other than wind. And this is where we turn up our natural gas power plant. And on the other hand, if you have a high supply but low demand, this is where we have to curtail, which means that the grid, electricity grid companies are paying wind farms to basically turn off the wind turbines because they cannot take the electricity. And that sometimes can result in negative pricing. So the grid companies are paying for electricity not to be generated. And if you look in the middle of the plot, I'm highlighting two potential areas. You can, for example, shift the resources. So right around, say here, February 24th at noon, you have high wind generation. And then at midnight, you have low wind generation. So if you can move the electricity around by that 36-hour period, that can also provide additional revenue to the grid companies. One other application is frequency regulation. This slide is showing quite a bit, but let me just tell you that regulation in frequency happens on a very fast time scale. So this is typically on the order of seconds. And so these various plot basically shows how effective it is to match the frequency of the electricity to the between the demand and the supply. On the top right, you have a case where you have battery-based buffering. So the two curves are matched perfectly. So there's no lag behind between the supply and demand. But if you go to, say, something like a hydro storage, so this is using water by pumping up the hill and down, you have a slightly greater mismatch because of the lag time in providing the electricity. And then if you look at a turbine-based combined cycle on the very lower plot, there you can see that the lag is even greater. So this tells you that the ability to maintain a very stable grid has to do with how fast you're able to buffer the electricity. And battery provides a really good way to do so. And this can directly generate revenue for the electricity grid. So here's one example. Many of you might have heard about the installation of a 100 megawatt, 129 megawatt hour battery system in Australia that was installed by Tesla in 2017. The main application of this battery system, which is based on lithium-ion batteries, is to provide for frequency generation, which means it's used to buffer the electricity so that the frequency is held constant. So 100 megawatt or 121 megawatt hour is not a very big number, but it is very exciting to see even a small installation like this can have a substantial impact on the type of storage used for frequency regulation. So if you look at the right, the plot, the first bar shows you Q4 in 2017, right before the installation of this battery system. You can see battery was a very small percentage of what's used for frequency regulation of the grid and is mainly powered by coal and hydro. Okay, so you're using coal and water to provide the buffering needed to regulate the frequency of electricity in Australia. But just the next quarter, so 3 months later, you can see battery grew from about 1% to over 10% as the mean to regulate the frequency of electricity. So a small installation like this one can have a huge impact, and this is for Australia as a country. So this is very exciting to see how a small battery system can have such a large impact for frequency regulation. Another application that I alluded to earlier is peak shaving. So let me get into some detail here. So peak shaving basically reflects the mismatch between the consumption of electricity and the generation of electricity. And here, because the generation of renewable electricity is variable, you have to buffer the differences between the two. So one application of peak shifting is as follows. You have the top of the demand at about 6 p.m. This is when everyone goes home, turn on electricity, maybe turn on the AC if you're in the summer in the southern states in the US. And at nighttime, for example, the electricity demand is much lower. So one idea is that you can generate excess electricity when you have lower demand and shift it by about 12 hours to higher demand. One particular application could be in storing wind electricity. So wind often blows at night. So if you're able to store that, basically you can charge your battery at night, and then you discharge the battery during the day when the demand is higher. This will lessen the demand on the electricity in the peak hours. So the ability to shave this peak can stabilize the grid and make it more economical for the grid to be operated. So one example of this peak shaving is the California Duct curve. Some of you may have heard this in the popular press. The Duct curve basically shows you the shape of the generation of non-renewable electricity and how it varies throughout the day. So if you look at the plot on the left, it is showing you the generation of electricity from non-renewable sources. Okay, so these are primarily your natural gas power plants in California for a typical spring day. And the curve on the top in gray is the actual in 2012. And as you go down, it shows you the prediction to 2020. And the prediction was made in 2013. So you can see that because the solar installation was still quite low back in 2012, so your generation of non-renewable electricity is fairly flat during the day. But as time went on, the solar installation increased in California, which means you're outputting much more renewable generation during the daytime. And as that renewable generation went up, that means the generation of conventional electricity from natural gas and others have to go down, okay? And that's why from 2012 to 2015, you're seeing the formation of the site profile of a duct, which tells you that you're needing less electricity during the day because you have more solar electricity to work with. What problem does this give you? Well, you have to shut down the generation of non-renewable electricity during the day, and you have to turn it back up right around 4 to 5 p.m. when the sun is beginning to set. And that gives you the neck of the curve. And if you look at the number here, we're talking about the ramping of approximately 10,000 megawatt over a 3-hour period. And this is a tremendous challenge, and it's a stress on the grid. And this was the prediction back in 2013. How good were the predictions? Not very good. In fact, what we are today, we're already way past the 2020 projection in terms of the duct curve. So we're very close to the bottom of this curve, which means we are shutting down a tremendous amount of conventional electricity generation during the daytime, and we have to turn it back up over a 3-hour period. And the plot on the right just shows you how much ramp we're talking about, 10,000 megawatt. To put some context, 10,000 megawatt is half of the Australia grid. So in California, we have to turn up electricity that is equal to half of the grid utilization in Australia. So this duct curve is a tremendous consideration when it comes to technologies that can mitigate the duct curve. Let me show another example of curtailment. So this is a projection in 2020 for the Western grid in the United States, showing how various forms of electricity, various forms of generation for electricity. So at the very bottom, you have nuclear. So that is very steady over time, so it doesn't vary. So the power plants are running uniformly. Then you have coal and hydro. So you can see coal actually goes down during the day, and the reason is very simple. The grid company turns off coal first because it has the largest carbon footprint. And the reason you turn off coal is because during the daytime, you have the increase in solar, and that is captured in yellow there. So this essentially shows you the different types of electricity that is being generated day to day. And if you look at the very, very top, there you can see curtailment. So there you have so much electricity that you couldn't turn off enough of the coal and other conventional generation so that you have to curtail the renewables by paying the renewable generation company not to generate, to turn off their resources. And this is a hit on the economics because the grid operator are paying money to the renewable generators, and the renewable generators are not able to generate the revenue they originally wanted to generate when they installed the equipment. So this shows you how dynamic the grid is. It's really incredible to see the ups and downs of various generation of electricity throughout just one day. And as another example of resource shifting, these plots are showing you the resource and demand profile on the left for California and on the right for the United States for the entire year, okay? So you can see the demand is fairly flat, okay? In California, it's fairly flat, and the US is a little bit less flat, and that is the orange curve there. But what is very interesting is if you look at the renewable electricity, so that's in blue on the left, and on the plot on the right is separated into both wind and solar in purple and yellow respectively. And there you can see a significant mismatch. You can see that we have more generation during the summer month and less generation over the winter month. So the opportunity here is, can we align our resources with our demand by shifting electricity around seasons? So can we take some of those electricity generated in the month of May to August, and we can shift that to the consumption in the winter, okay? So this is something that is not yet possible, but seasonal shifting of electricity is a huge opportunity. And as I commented on earlier, if we want renewable to penetrate the grid completely, we have to tackle this challenge. These are a few more plots of simulations. So what this is plotting is basically how much capacity overbuilding we need. 1 means no overbuilding, and 2, 3, 4 means we have to overbuild the solar and wind by a certain amount. And the x-axis is showing you the amount of renewable penetration. So 0 means no renewables, and 100 means completely renewable. The black curve shows you the amount of overbuilding if you have only have no storage. And as you go to the lighter green curve, it shows you what happens if you have storage 1 day, 4 day, and 1 month. So as you increase storage, then you get to decreased amount of overbuilding of solar and wind. And the reason is simple. If you don't have storage and you want a certain amount of renewable penetration, that means you have to have more than you need, so then you can generate enough solar and wind when the sun is not shining or when the wind is not blowing. But if you have storage, then you're able to shift the resources around so that even when the sun is not shining and the wind is not blowing, you can still use the renewable, and that decreases the amount of overbuilding that is required. And it's very interesting to see the various cases. The top curve shows you what happens if you purely have solar, okay? Because solar is intermittent on a daily basis, this highlights the importance of storage. So if you want 50% penetration of solar in the United States, that means you need to have storage. Without it, you can only get to approximately 50% penetration when it becomes impossible to supply. And this is simply reflecting the fact that the sun doesn't shine at night. But if you look at the bottom cases, if you go to 50-50 mixture of solar and wind, the curve shifts to the right, which means for a given amount of penetration, you need much less overbuilding. And this reflects the fact that wind is intermittent on a different time scale. It's intermittent on several day basis. So if you mix just the right amount of wind and solar, you're able to have less overbuilding for a given amount of penetration. And if you go to 100% wind on the bottom, that also showcases as well. But regardless of what scenario you consider, you need to have storage in order to reach high degree of penetration of renewable electricity in the grid system. So now let me talk about the alternatives. So we talked a lot about the various application and the business need for storage, whether it is seasonal storage, whether it's daily storage or peak shaving. Energy storage is not the only way to do it. There are a lot of competitions that is already available today. And probably one of the most attractive alternative is natural gas peaker plants. So a peaker basically reflects the fact that these natural gas power plants are not turned on all the time. It is turned on when the demand of electricity increases, for example, around 3 p.m., when the generation of renewable goes down. And this is basically showing you the cost of electricity per megawatt hour shifted. So this is talking about if I have to move 1 megawatt hour of electricity around for a certain amount of time, what will be the cost? And you can see, actually, technology like lithium-ion battery is high on this plot, okay? And using a natural gas peaker plant is actually very cost-effective. This is based on today's cost of lithium-ion battery technology. But look at the same plot on the right. In 2030, the projection is that lithium-ion battery will actually become less expensive than natural gas power plants. So this is showing you the importance of continuing to push the cost of battery technology so that it can compete with other ways of shifting electricity, for example, through peaker plants, on cost. Okay, and I want to emphasize this one more time, is that for something as enormous as the grid, techno-economics is the principal driving force. You have to think primarily about cost. So now let's get into the technology aspect. So if we want to shift energy around, whether it is on the order of an hour, 3 hours, a day, or across the season, there are many different metrics that must be satisfied at the same time. And this plot here shows you just a few of those metrics. And I'll walk you through from the top, starting with calendar life. So calendar life basically tells you for a particular energy storage technology, how long can you use it for? It doesn't matter how many times you use it, it's just a calendar. So is it 10 years, 20 years? And this determines the cost of electricity that is amortized over the lifetime of the technology. Going around in the clockwise fashion, the next one is cycle life. So this is how many times you can cycle the battery. So if you're storing electricity on a daily basis, then you will need to cycle it about 300 times in a year. If you're doing frequency regulation, like the Australia example I showed earlier, then you're doing multiple cycles or tens of cycles a day. The next one is energy cost. So this is basically looking at how much does it take to store a certain amount of energy. So this will be the dollar per kilowatt hour that I have shown earlier. The next one is energy density. So this is how heavy the technology would be given an amount of energy stored. The next one is power cost. So this is looking at the cost of delivering electricity at a certain rate. So for those of you not familiar with energy and power, in the context of an electric vehicle, energy tells you how far you can drive the car, so that's the range. And the power basically tells you how fast you can either charge the car or how fast you can accelerate the car. So there are costs associated with both. Keep going clockwise fashion, ramp rate. So this is reflecting how fast you're able to charge and discharge the particular energy storage technology. So we talked quite a bit about the Duct curve. So that particular application will require you to be able to charge and discharge the energy storage technology over hours. But if you're talking about frequency regulation, that period can be quite a bit shorter as well. Round trip efficiency, this is basically telling you how much of the electricity you put into the technology you can actually get out. So for a 100% round trip efficient system, that means every bit of energy you put in, you can take out. And this also determines the cost of storage as well. Safety is very important. You want to have an energy storage technology that is safe over the lifetime of the system. And this applies for both large-scale utility installations and also home or transportation. Temperature range is important. We have many participants here from different parts of the world. Sometimes it gets very hot in the summer, sometimes it gets very cold in the winter. To have a technology that performs over the broad range of temperature, and those of you who have electric vehicle can appreciate the fact that in the winter months, then your performance is decreased, for example, for lithium-ion battery, and that highlights one of the weakness of that particular technology. And the final one is the volumetric energy density. So this is how much you can store per size, okay? So that, in combination with the gravimetric energy density, basically tells you how big and how heavy the particular technology has to be. The challenge with energy storage technology is that you have to satisfy many of these at the same time. And the plot in the middle basically shows you two example technologies in which you don't have complete meeting of all the metrics, okay? So there's no silver bullet. And depending on the application, you can weigh these metrics differently. So for example, for transportation, gravimetric and volumetric energy densities are very important. But for grid application, the calendar to life is very important. So as I will talk about in the next 10 minutes or so, is really thinking about what use case you would like a particular technology to serve. And depending on the use cases, the technology will be different. And there is no silver bullet. So this is why we need a wide range of energy storage technology to meet the different type of applications that we have. So this is my personal view and classification of energy storage technologies. I divided them by the physical storage mechanism. So going from the left, we have electromagnetic. These will be technologies such as supercapacitors. We have thermal storage. So this is storing energy in the form of heat. This is most notable in the form of molten salt that is used for concentrated solar power, whereby you concentrate solar light and you generate heat, and the heat can be stored by heating something up like a molten salt. The next one is probably the one that has received the most amount of attention is electrochemical. And the poster child of electrochemical storage is lithium-ion batteries. But you also have a wide range of other battery technology, lead acid, flow battery, and so forth. Further on the right, we have mechanical. And the poster child for mechanical is pumped hydro storage. So you take electricity, you take water and you pump it up the hill. That's how you charge up a pumped hydro system. And then water goes down the hill. This is how you get electricity out. You can do this not only with water, but you can use air as a medium. And you can also use other things as well, masses, rocks even, by moving up and down the hill. And the final one is chemical. So we have also the opportunity to take electricity and generate chemicals such as hydrogen, and then we can combust it subsequently and then to make electricity again. So these are the various aspects. I don't have that much time today, so I'll only briefly highlight a few examples, but I would like the audience to appreciate the wide range of technologies that are being investigated today at universities, national labs, and industry to try to get this work at the scale I alluded to earlier in my talk. So let me look at the installation capacity by energy storage. By far, the technology of preference today is pumped hydro, okay? An overwhelming amount of energy today are being stored by pumping water up and down. If you look at other forms of storage, thermal, electrochemical, or other, it's very small. It barely shows up on the plot on the left. And the plot on the right basically shows a blow up of those three things, okay? So technology other than pumped hydro. So there you have a significant participation of thermal storage, so storing energy in the form of heat. Lithium-ion battery is the biggest one now in the electrochemical area. And you also have other installation in mechanical, for example, storing it in compressed air or by turning the wheel around and spinning it. The opportunity for the future is how can we develop different technology to reach the same level of economy as pumped hydro and ultimately to exceed it. And the reason why pumped hydro has limitation is because it's geography dependent and water resource is always a consideration as well. But let me get right into lithium-ion battery. This is something that has really captured the attention of the public in the past decade because of the rapid explosion of electric vehicles. A battery technology is actually fairly straightforward. You are shuttling atoms such as lithium between a low energy reservoir and a high energy reservoir. So in a manner of speaking, this is not very different than pumped hydro, except the energy carrier is not water and pumping up a difference in height, but is really a lithium that is being pumped around a difference in chemistry between the two sides of the battery, which we call the negative electrode, sometimes called the anode, and the positive electrode, sometimes called the cathode. So the ability to move this energy carrier lithium around the two electrode is how a battery works. One of the most attractive things about a battery is how inexpensive it has become. So if you look at the table on the top right, it shows you the various parameters for the technology. Currently, we are looking at greater than 2 gigawatt of installed capacity. Typical duration now, based on the economy, is about 1 to 4 hours for grid, and that's already serving the need of electric vehicle. The lifetime is about several thousand recharge cycles, and the calendar life could be on the order of about 10 years. Round trip efficiency is very high, about 90% of the electricity you put in, you can take it out. The cost is extremely attractive today for transportation, but it is quite far from what is needed for the electrical grid. I didn't get into the economics of the grid, but if you want to have a significant penetration of electricity storage using battery, you need to look at significantly under $100 per kilowatt hour for diurnal storage, meaning across day. And if you want to look at, say, storage across several days or a week, you need to reach about $20 a kilowatt hour. So we're still about 20x off to reaching that goal. So new technology is certainly needed. And probably what is most impressive in lithium-ion battery is the scaling exercise that we have went through. So the plot on the left shows you the dollar per kilowatt hour on a battery pack level. It's gone from over $1,000 per kilowatt hour just in 2013 to now slightly anticipated to below $100 by 2025 and approaching $50 per kilowatt hour. So this is extremely attractive. As the cost goes down, new applications will come up. So as the cost down, then you can store electricity for longer periods of time, for example, for the electrical grid, and the cost of transportation for EVs will also go down as well. And the cost decline will be matched with the growth in the installed capacity, and that is what's shown on the right. It is truly exciting to think that the lithium-ion battery market should, in the next 10 years, reach over $1 trillion worldwide. This is a plot showing you the companies which are involved in manufacturing lithium-ion battery. A majority of these companies are in China, some of them are in Korea, and elsewhere in the world as well. And most companies have been announcing new capacity, so this plot is already outdated, and we're seeing numbers even larger today in order for the industry to meet the demands for transportation and increasingly for grid storage application for lithium-ion batteries. So what is the ultimate limit of the cost of lithium-ion battery? So I showed a projection down to $70 and $50 a kilowatt hour. So fundamentally, what sets the floor of the cost of battery technology is the material cost. So this bar shows you the projection of costs from 2015 to 2025. So you can see the cost of manufacturing, the cost of assembling the batteries into a pack will continue to go down. But the cost of the material will not decrease dramatically. So the material costs will set the cost floor. So basically, if you look at the projection going forward to 2025, the material costs will dominate the cost of the battery pack. So this is showing you the trend in the elemental cost. This is the sum of the three expensive components in a battery, so cobalt, nickel, and lithium. And you can see because of the rise in demand, you have now a sudden rise in cobalt price over the past few years. And this is going to be a significant constraint. So one opportunity is, can we design new battery chemistry that do not use these expensive elements? And this will be one pathway toward lowering the cost floor, which is set by the material cost. Another thing to think about for batteries is cost that is levelized by the lifetime. So the cost I've been showing so far is levelized only by the energy, so dollar per kilowatt hour. But different battery technology have different lifetime. So for transportation, we need maybe 1,000 cycles. So if you think about a car with a 250-mile range, 1,000 cycle means it's a 250,000 mile, and that likely exceeds the lifetime of cars in most use cases. But for grid application, we need much more. We need thousands or 10,000 cycle life. And when you start dividing the cost by the lifetime, the equation changes. So for example, this plot shows you different technologies in terms of the cost per kilowatt hour and the cycle life. Some of these technologies are not used in transportation today because the energy density isn't high enough. But if your primary consideration was not the energy density, say you build a big battery system in the desert or elsewhere, then you have to actually worry about cost more than the density. And the plot on the right that shows you, once you levelize the cost by the cycle life of the battery, then different winners emerge. So the present technology we use today are actually fairly high in the levelized cost because you're trading the lifetime of the battery for high energy density. But for certain use case like the grid, you may want a lower energy density, but a much longer lifetime. And there are new chemistries out there that can potentially deliver that combination of metrics. So this is something else to think about too, in terms of developing the right chemistry and the right technology that will hit the needs of the market. One other application that is emerging is second life batteries from electric vehicles. So as we have more and more electric vehicles on the market, eventually we'll have them coming off electric vehicle. Maybe they won't be good enough for transportation, the range is too short, but we can still take them out and use them in grid application, for example, by using them to buffer electricity for solar. And these simulation basically tells you that by the beginning of 2020, we will begin to see significant amount of battery come off electric vehicle. And this second life use of batteries represents a very large market as well. And the economics is not fully understood. And there's a lot of opportunity in thinking about how do we effectively take batteries out of electric vehicles and repurpose them for other applications such as the grid. So I'm out of time today, so maybe I would just say a few more words. I didn't have time to get into the specific technologies here. The take-home message here is there are a lot of different technology, and each one of them will have a different metrics. It will not meet all the requirement. There's no silver bullet. R&D is ongoing for everything I'm showing you here and more. And let me stop with this take-home message here, which is looking at the big opportunity. My opinion is that we cannot work on technology without considering the business needs and the use case. So I spent about half the talk talking about the various use cases, how the grid companies could be using battery to generate revenue. We can be looking at transportation as a way to replace internal combustion engines. We talked about the economics behind it. On the right-hand side, we have the technology. I only talked about electrochemical today, but there are many more. And really, it is about matching the two finding the right technology for the specific business cases, and identifying the need to further develop technology to meet certain techno-economic goals. And I think this is what is needed to really see the penetration of renewable electricity and the role that energy storage will play. So let me stop here, and thank you very much for listening.
Now we have a few minutes for Will to answer a few of your questions. All right, so the first question is, what are the challenges to recycling batteries at a large scale? And what are the associated environmental impacts? How is technology reducing the environmental footprint?
This is a very loaded question, I must say. So let me answer the last question first. The environmental footprint is not an easy question to answer. You often, see on the license plate saying this is a zero emission vehicle. That is not entirely true. It depends on how the electricity was generated. And you need to think about how much emission went into making the technology. So here at Stanford and elsewhere, folks are doing analysis on the life cycle footprint of these technologies. So as you compare different technology, you have to think about what is the emission that went into the extraction of the raw material, the manufacturing, and the assembly of the technology, and that have to be considered. There's no simple answer, and one can simulate what the carbon payback time you would have for a particular technology. So definitely battery, it is not a zero emission technology if you consider the lifetime. The other aspect from the listener is recycling. This will be crucially important. It will be a huge industry. And let me comment on it from two perspectives. First is economics. So recycling will only be done if it's economically viable. And it will be economically viable, for example, when the raw material cost goes up. So people will be developing ways to recycle the battery so that can be sold. So if you think about the budget for recycling, it's basically how much you get paid for the material that you extract. On the engineering side, recycling is very interesting. When you think about recycling, you think about boiling it down to the fundamental building blocks, maybe extracting cobalt again, that's the most expensive element in a battery, but this is very challenging. So one big opportunity could be, can we recycle battery without having to reduce it down to the original makeup of the battery? Can we, for example, think about rejuvenating a battery or regenerating a battery as a way of recycling and reuse as opposed to deconstructing the battery? And one also have to think about the safety of recycling. So how do you take apart the battery safely? And how do we design battery for recycling? So can we design it with recycling in mind so the form factor already allows easy recycling?
Great, thank you so much. Here's an interesting one that I pulled up. So this participant wrote, California recently announced requiring solar panels on all new homes beginning in January 1st, 2020. What are your thoughts on the effects of overgeneration and potential curtailments from this happening?
The overgeneration is already there. So as I showed in the Duct curve, we have to ramp up half of the Australia grid in 3 hours in California. This is how significant the problem is. So this is only going to get worse. And storage is an obvious answer. But let me discuss just briefly what companies, say, for example, in California, PG&E and Southern California Edison are doing. So there are a lot of legacy power plant based on natural gas. And one way to do it is to simply power up the natural gas power plant. The hardware is already there. They're not being fully utilized. So that is the easy way. Battery-based technology or other technology is important as well, but currently the investment needed to get that up and running, basically the capital expenditure needed is enormous. So looking forward, I think one thing that the policymakers should consider is, as we mandate more and more renewable electricity generation, we must also create policy to give incentive to more storage. And we're seeing this already. For example, in California, we have this self-generation credit that give several $1,000s to homeowners to install a battery system at home. So these are sort of complementary policy that have to be looked at. I didn't really mention the policy aspect today, but that's another huge opportunity, is to think about the role of policy in terms of shaping how renewable technology, including generation and storage, will be deployed.
Great. Thank you so much. Last question, and I think a few people actually asked this one. So how can I get involved in this field, especially if I have a lot of global experience in power, but I don't necessarily have startup money or startup experience? How could I, as a professional, get involved in energy storage?
Yeah, I think this is also a very difficult question to answer. I think you have taken the first step. Energy storage is extremely complex and it is rapidly evolving. It changes by the month. There are new technologies emerging all the time. So my recommendation would be to get caught up by learning more about the technologies we have today and continue to follow it. There are many startups here in Silicon Valley and elsewhere pursuing the development of energy technology. But I think as people who are interested in the technology, you have to be able to assess it. So what market is the technology addressing? What are the economical driving forces? What are the availability of scaling up, right? You hear a lot of popular press and a lot of hype around, say, battery technology. But I think one important skill to have is to be able to look at the technology and say, okay, this is really going to have an impact at scale, or this is hype. And I think this is one of the things that you can try to learn, for example, from our program here.
Great. Well, thank you so much, everyone, for joining us. We will be sending out a copy of this presentation within a week. And thank you all, and we hope you enjoy the rest of your day.
Thank you.